So, now let us see the gravitational field due to a solid sphere. So, we have a solid sphere here and we wish to calculate its field at inside point and outside point. So, first case 1, outside points. So, in order to calculate the field at an outside point, we take a point P at a distance r and then consider a spherical concentric Gaussian surface. Now, this sphere is of radius r and this is the mass is uniformly distributed throughout its volume. So, consider a spherical concentric Gaussian surface of radius r greater than r. So, let us apply Gauss's theorem here. So, what we expect due to this sphere, due to symmetricity, G is radially inward, gravitational field G is radially inward. So, if we have G dot ds, that is equal to minus 4 pi G m enclosed. So, you see G is everywhere constant and you see, suppose I take a area, this area vector is here, this area vector dA is here and G vector is here. So, if I take the dot product, there will be a minus sign. So, minus, you see G comes outside and it will be 4 pi r square minus 4 pi G. Mass enclosed is the total mass m. Suppose this has a total mass m. So, G becomes 4 pi cancels, G m by r square. So, the gravitational field due to a solid sphere at an outside point is as if the whole mass is centered, is a point mass placed at the center. Now, let us see the field inside the mass. Now, let us consider the inside points. So, you see this is our massive ball of mass m and radius r. So, this time we are going to construct a Gaussian surface inside it. So, this is R and this is my Gaussian surface. So, consider a concentric spherical Gaussian surface of radius small r, that is less than this time r. Now, you see here, since mass is inside and outside this Gaussian surface, so we expect due to symmetricity that G will be acting inward. So, if we have G dot ds is equal to minus 4 pi G of mass enclosed. So, G comes here minus G, ds means 4 pi r square minus 4 pi G. Now, what is the mass enclosed here is, suppose mass density is rho, then 4 by 3 pi this small r cube. So, we have this 4 pi cancel, this minus gets cancelled. So, G becomes, this r square is there, rho into 4 by 3 pi r, this and one G is there. So, now rho is here, you see capital M by 4 by 3 pi r cube. So, that we will substitute G into 4 by 3 pi r, that rho is 3 m by 4 pi r cube. So, this G becomes, this 4 pi gets cancelled, this 3 cancels, G m r by r cube. So this is G for inside points. So let us summarize the results. So we got G is equal to, in parametric form, GM GMR by R cube if R is less equal to R, and it is GM GM by R square if R is greater than R. So for inside points this formula, for outside points this formula. Now let us see in graphical form how to represent this function. So this is my mass of radius R. So you see here, here R is plotted along this x axis, and here we are going to plot G, magnitude of G vector. G is a vector quantity. So you see here, up to this place, that is small r becomes equal to R, this G uniformly increases to the maximum value, that is Gm by R square. Gm by R square. Next, it decreases as 1 by R square. So it decreases. So here G is proportional to 1 by R square, and here proportional to R. G is proportional to R, here proportional to 1 by R square. So now let us take an example where we are going to use principle of superposition and some symmetricity. So we have a massive ring of mass per unit length lambda. So this is mass per unit lambda is there, and due to this massive ring, at the center I have a gravitational field along this direction, that is suppose G naught. So the gravitational field due to this massive ring is G naught. Now what we do, we have taken a cutout of this portion. So now I want to know what is the gravitational field due to this cutout at the center. So there will be a G field here. How much is this G, that we have to calculate, given this angle is alpha. So this is our situation. So let us solve this. Now what we expect from symmetricity, that the net field here will bisect this angle and this angle. So these two angles, because of symmetricity. Now because of this portion, the field is somewhere here which bisects this angle. So if total angle is alpha, this is alpha by 2. Let us draw a fresh diagram. So this is my problem part, let it be here. So let us draw this side. So this is this part, and this part, that which is making an angle alpha, that G due to this part is G here, that is alpha by 2, and here also alpha by 2. Now if this part will apply a field here, that will also bisect this angle. So the contribution due to this part is also somewhere here. So that this angle, you see this angle is alpha, this angle becomes 180 minus alpha. So this angle becomes 90 minus alpha by 2. And this is, suppose I say this is G1, this is G2. G1 is the field due to this portion, and G2 is the field due to this portion. So together this portion and this portion applies G1 and this portion applies G2 field. So according to principle of superposition, the total field here due to these two is already given as G naught. So I can write G1 vector plus G2 vector is equal to G naught vector, which is given already. We wish to calculate G1. Now we see this is alpha by 2 and this is 90 minus alpha by 2. So, this is 90 degree. This is 90 degree. So, if this is 90 degree, you just see this is G naught, this is alpha by 2, this is 90 minus alpha by 2. So, this is alpha by 2. So, now you see this is also, this is a rectangle we can see. So, alpha by 2, so this becomes G naught, G1 then becomes, let us write here, G1 becomes G naught sin alpha by 2, sin alpha by 2. So, this is our answer. So, as you see here, the total field which is G naught is the sum of this field and the field due to this portion, that is G1 and G2. Vector sum of G1 and G2 gives G naught. And we have further used the symmetricity idea that if this is an arc, then the gravitational field here will bisect these two angles. So, with the help of symmetricity and superposition, we are able to relate the field due to this ring at the center and due to an arc at the center. So, now let us take another example in which I have a massive rod. Suppose this is a massive straight rod extending up to infinity. It extends to infinity, suppose. And here let us consider an arc like this which extends to 90 degree, and you see this is the arc, 90 degree arc like this. They are just touching. So, now let us see what we want to explore is if this arc subtends the same angle at its center what this rod subtends, then the gravitational field due to this arc and this rod is going to be the same. This result we want to get. So, what we will do? We will consider from here an angle theta and such that, so this is theta and this is the theta angle, suppose. So, suppose this is A, this portion B, C, D, E. If I draw perpendicular F, then G. So, let us compare this is the element on the curved section and this is the element on the straight section. So, element here you see this is on the straight section. So, let us compare the gravitational influence at A due to this curved section and this straight section. So, that is compare. So, we wish to compare DG arc and DG line, straight segment. Arc means up to BC we will say, and we will see that how these gravitational field due to these element and this element will be at A. We are comparing the gravitational influence of this BC element and DE element at A. So, I will take the ratio. So, DG due to this arc by DG due to this line segment, this gravitational field due to this element is G lambda BC by AB square upon G, this is mass. So, here mass of this is lambda DE by this distance AD square. So, this is the ratio, that DGA by DGL. So, GG lambda cancel, we will get BC by DE into AD square upon AB square. So, BC, BC is okay. DE, can we write DE as this angle is theta? So this is 90 minus theta. So this is theta. So DE can be written as, so from this triangle you just see this triangle DE, this is E and D, this angle is theta and this is F. So cos theta will be written as DF by DE. We want DE. So DE is DF by cos theta. DE is DF by cos theta. So cos theta will be here. And AD square, this is AD square by AB square. So now you see what we got. Now you just see this triangle ABC and ADF. These two triangles, if I have drawn a perpendicular here, then are similar. So BC by DF, this by this is AB by AD. So this will be replaced by AB by AD. Next cos theta into AD square by AB square. So you see this AB square, this square AD cancel. So we got cos theta is equal to AD by AB. AD and AB. AB, this is an arc, so AB can be written as AG. So I will write cos theta into AG upon AB. Sorry, this is AD. This is AD. AB is written as AG. So AG. That will be further written as cos theta into AD. AD by AG is sec theta. Sec theta, that comes out to be 1. Therefore, we have got a very important result that if we have an arc, you see, if this element and this element which subtend the same angle produces the same gravitational field, that means if whatever the d theta is there, that means if we have an arc and if we have a line segment so that they are equidistant from A, then if they subtend the same angle at A, then they will have the same gravitational influence. In that case, that arc can be replaced by this line segment and this line segment can be replaced by this. So this is very, very important result. So now let us see what is the field due to a massive ring at its center. So this is the massive ring and we wish to know what is the G0 field here. G0. So we will use the previous lemma. So what we will do? We will draw a tangent from here, this way and this way, so that you see here this arc up to 180 degree, this total arc, that is a semi ring, subtend the same angle which this tangent extending to infinity subtend at the center. So the center is equidistance, the center is equidistant from the arc, that is the semi ring, and the tangent extending to infinity on both sides. That means they are going to produce the same field. Now already we have discussed the field produced due to a long slender rod at this point is given as G is equal to 2G, where lambda is mass per unit length, by, suppose this distance is y, so by y. So this was the formula we have already derived in our first session. So what G0 we get, is equivalent to, that is 2g lambda by r. So, thus once I know a single expression that due to a infinite rod what is the field, that means this arc and this rod produces the same gravitational field at this. So, due to this arc also we have this field. Let us generalize this result to calculate the field due to a massive rod at a general point. So, let us do now this, the field due to semi-infinite rod. So, this is a infinitely long rod here, and we want to know what is the field at this point. So, we expect the field to be like this. So, you see, just recall that the field due to this rod is somewhere here. How much that field is, this we want to calculate. So, we will use our previous lemma, the result that this infinite rod is and this arc, if they subtend the same angle at their center, then they are equivalent. So, you see, this is extending to infinity, that means I can assume that this is equivalent to a right angle arc. Now, due to a right angle arc, the gravitational field will be here G, that will be given as, suppose this angle is 90 degree. So, just recall this expression that if we have a 90 degree arc, it has G naught, and due to this alpha angle arc, we have a field here, that is G is equal to G naught sin alpha by 2. So, in this arc, this angle is 90. So, we will write G naught sin 90 by 2, that is 45 degree, that is G naught by root 2. Now, what is G naught? G naught is the field due to this whole semi ring at this point. Now, this semi ring and this infinite rod has the same field. So, we will write this G naught as 2g lambda by r, and this 1 by root 2, that becomes root 2g lambda by r. So, this g then becomes how much? Root 2g lambda by r, and you see this will be bisecting this angle, that means 45 degree from here and 45 from here. So, g will be root 2g lambda by r for this semi-infinite mass. Now, let us calculate the field due to a massive straight rod at a general point. In the first session we learnt the field due to this massive rod at a equatorial point. Suppose this is a rod we consider at this point, but not at a general point. Presently, let us see, suppose this is a general point P. I wish to calculate the field due to this rod. This rod is here, gravitational field due to this rod. So, now you see, if we use calculus, unnecessary we have to take so much care of the integration. So, by using a lemma, the previous lemma which we have derived, we can easily calculate. Now, it is given that this distance is suppose y, and this distance is given as a, and this given as b. So, these are the dimensions of the rod, and the location of P must be known. So, if I draw an arc here, you just see this, draw this, join this and this. So, you see, I can say that if this is another rod in the form of an arc, then this rod and this rod produces the same field at the P, and how much this will produce, that will bisect the gravitational field here G, due to this will bisect this angle, That means the field due to this arc is equal to the field due to this. So, G will be simply how much? So, the field due to this arc. Now this arc has the field due to an arc has an expression G is equal to G naught sin alpha by 2, where G naught is the field that we have seen, the field due to a semi ring, where G naught is equal to 2 G lambda by R. So here we will, the G naught will be 2 G lambda by R means here Y. So we got G naught. Then sin alpha by 2, then sine of alpha by 2. So sine of some angle. What angle? This angle. This angle means this total angle H. This total angle can be written as tan inverse this angle H B by Y. B by Y. This total angle minus this small angle, this angle becomes minus tan inverse A by Y. So you see here we got this expression. So without any calculation, just by using that lemma, we have derived the result for the general expression for the gravitational field due to a finite rod at a general point. So you see this lemma, that these two lemmas, that if we have a ring and if I cut out a portion of that ring and with an angle alpha, then the G due to this will be equal to G naught sin alpha by 2. This lemma, and another one, that if we have a linear segment and an arc which subtend the same angle here at a point which is the center of the arc, then the field due to this and this is going to be same. So together with this lemma and this short result, we can derive a lot of results and problems very easily. Now let us take an example where we are going to use principle of superposition and some different concepts. So we have here a sphere. We have a sphere, and inside this uniform sphere we have a cavity. Suppose we have a cavity here. So the cavity is displaced from the center of this sphere by a distance a. This has a radius r, and you can assume that this has a small radius r. So you see we have this mass something like this, and in this cavity, this is cavity. So we want to find out the field inside this cavity. So determine the gravitational field inside the cavity. So let us explore the field within this region. So here the basic idea we are going to use is this mass with the cavity inside it is assumed to be the sum of a uniform ball plus another ball. Now you see, let us introduce a hypothetical concept of matter and its counterpart antimatter. Now antimatter theories are very popular. Presently they are not confirmed. So you see, I say the normal matter is denoted by, suppose I say plus sign. So I will say plus matter means normal matter, and when there is antimatter, I will say it's minus, negative mass. In fact, it is not confirmed. We don't know whether mass is negative or positive. Presently our knowledge is that we have only one mass, that is matter. Now let us just imagine, only for mathematical sake, that there are two types of masses. One is called positive mass, another is called negative mass. So when we have a positive mass of ball and if I place a negative mass of ball, then this positive and negative mass will annihilate, matter and antimatter will annihilate, and you will get a cavity region. So our idea is to know what is the field here. Suppose I want a field here, general point, that means that point P lies here and that point is lying here. So due to this positive mass, what is the field here? So the field due to this positive mass will be like this, and due to this negative mass, so you see negative mass field will be something like this. So let us explore that this field is the sum of these two fields. Let us calculate it. So this is our basic idea, basic physics. Now we will calculate it. So now we require one formula for field due to this ball, uniform ball at an inside point. So we have already calculated. Let us calculate once more. Suppose this is the center and this is the R. So we will apply Gauss's theorem. G dot ds is equal to minus 4 pi g mass enclosed. So G is G here, minus G because G is inward here, surface area is outside, ds is here and G is here. So minus G 4 pi r square is more minus 4 pi G rho into 4 by 3 pi r cube. This is the mass enclosed. So 4 pi r square, simply 1 r will be there. So will be r cube is there. So 4 pi cancel, G will be equal to 4 pi G rho by 3, 4 pi G rho by 3 r, 4 pi G rho r by 3. So G is proportional to R. One more point, that matter and matter attracts. So we will use this, matter and matter will attract. So matter and antimatter repel, and antimatter and antimatter attract. So this is what the law for matter and antimatter will be. Matter attracts. You see, all masses attract because all masses we have assumed matter. Suppose there is a hypothetical antimatter, all antimatters will attract also, but if a matter antimatter is there, that they will repel. So now you just see the field here. Suppose this is the cavity region and I want to know the field at this point. So what I will do, I will join these two. The field, this is a, let us take a field here. Field means we place a positive mass, that means matter, test mass. So this will attract here. So suppose this distance is r plus, suppose this is positive mass and this is negative mass. This is negative mass, this whole sphere is positive mass and this much negative mass. So this region is cavity region. So this will repel in this direction. So this is r minus. So the net field is the sum of these two fields, which is something like this, that we have to calculate. So G here is the sum of G positive plus G minus. G positive means here you see 4 pi G rho by 3 and its direction is here inward, that is this direction r positive. R, you see this is inward and you see this r positive is a vector I have drawn. Suppose I have drawn a vector like this, that is r positive vector. So this vector is, so I will write this as minus r positive vector, then plus G minus, this vector is, suppose here is r minus vector, radius vector from this to this, from negative to this is r minus vector. So it will be, this is, this direction of this will be 4 pi G rho by 3 r minus vector. You see direction is along r minus. So we have 4 pi g rho by 3 common, r minus vector minus r plus vector. So, you see this vector minus this vector is actually, this is a vector is actually minus a vector. So, this is equal to 4 pi g rho by 3 as minus a vector, minus a vector. That means a vector is this, so minus a means this. So, what is the conclusion? The conclusion is, if we have a cavity region, then the field is uniform inside the cavity and it is directed towards the center, from this center to this center. So, this is the final expression. The field is thus, let us write it, thus the field is uniform inside the cavity. This is very, very important point. The field is uniform inside the cavity. Let us see the idea of antimatter, how it can be useful to discuss the attraction. So, suppose this is a isotropic universe. This is a isotropic universe, that is a cloud of gas and which has two bubbles. You see two bubbles, you see this is two bubbles. So, you can see this region you can find there is no mass. So, just I have here I am drawing that circular, these are circular regions which have no mass. So, cavity, we can say they are cavity. So, this is the isotropic cloud of gases with two cavities. So, what will happen? The cavity will attract, repel. This is what we have to discuss. So, you see this is similar to our previous problem. So, what we will say? We will say that there is a universe, there is a cloud of positive matter plus there are two antimatters here. So, this is something positive mass and you see this is just a negative mass, you can say negative mass. So, this is antimatter. So, when you put this antimatter here, then you will get this region devoid of mass. So, in this way the superposition of matter and antimatter yields cavity. So, this is a very important point. Let us write it, superposition of matter and antimatter creates a cavity. Now, the role of antimatter is exactly opposite to that of matter. So, you see we have seen all the matter attracting. So, all this one will repel, sorry this one, all this matter attract. So, this will also attract. So, antimatter and two antimatter particles will also attract. Matter and antimatter will repel. So, this antimatter attracts. Now, you see I want to know what is, how this bubbles or how these cavities will attract, means they will come close, they will remain stationary or they will go far away. So, in order to know whether they attract or repel at this location and this location, what are the forces acting? You see, so this is C1 and this is point C2. This is C1 and this is point C2. So, what happens? You see, if there is a matter isotropic distribution of matter, then there is no force, there is no unbalanced force. So, due to this positive mass matter there is no force, but because of these here they will attract, that means the net force between C1 and C2 is attractive. Thus the cavities attract each other. This is very important point, and once this question was asked in our NSCP exam, Now let us see acceleration due to gravity. So you see, if we have a massive object somewhere here, suppose this is earth, and if I place an object here, that object is under the gravitational influence of earth, that I say g, that is equal to g mass of earth by this distance from the center r whole square into minus radial unit vector. This was g. Now if I apply force equal to mass times acceleration, so force is itself given by g vector, mg vector, that is mass by a. So mm cancel. So we say that the acceleration due to gravity is itself the gravitational field intensity. So thus the acceleration due to the gravity is equal to the gravitational field at the point. So actually both are same. So acceleration due to gravity is denoted by g. So acceleration due to gravity will be denoted by g. Next let us see what is the acceleration due to gravity on the surface of earth, and when we go to some height, how acceleration of gravity will vary, and when we will go in some depth, how acceleration will depend on the depth. Now let us see the variation of acceleration due to gravity with height. Suppose this is the surface of earth, and from the surface of earth we are at a height h. So depending on how much is h, so this is, let us write this distance from the surface of earth as h and from the center of earth as r. The gravitational field here, applying Newton's law here, mass times the acceleration g, at this place we have g, is equal to the gravitational force. Suppose this is mass m, so g m by r square, this small r. So we can, this is r plus h whole square we can write. So now this cancels. So we have g equal to g by r plus h whole square. Now g is equal to g by r square into r square by r plus h whole square. So you see, look at this term, at the surface of earth, if we have a mass m, then its weight will be mg naught, where g naught is the acceleration due to gravity at the surface of earth, g by r square, re square, r capital is ra, that is, so we have g naught is g by r square. Let us simply reserve the letter capital R for the radius of earth. So we will replace this here. So what we got, g is g naught r square by r plus h whole square. So this is our general expression. Now suppose if h is very less than r, h is very less than r but still comparable, then g will be equal to g naught r square by, you take this r common, so we will get r square 1 plus h by r whole square. This gets cancelled, so this becomes g naught times, we can bring it upward, 1 plus h by r to the power minus 2. Now let us write this side. So now g becomes g naught 1 minus 2h by r where we have used the binomial, expression. We will use the concept of 1 plus x to the power m is equal to 1 plus mx if x tends to 0. If x is small, then this can be written as this. This approximations we have taken here. So, the expression for g as you go up becomes g naught 1 minus 2h by r. Thus, g decreases as we go up. And how it decreases? This is given by this relation. Now, let us study the variation of g with depth. So, suppose we are inside the earth, we have inside a mine which is at a distance d, depth d. So, when we are inside here and I wish to calculate g at this location, then what we do? Already we have seen from Gauss's theorem that the mass of this side will not contribute to g here, the inside masses will contribute. So, once we are inside the earth, then the outer shell will have no influence on g. That is the shell theorem which tells that because of that shell there is no inside field. So, the inside contribution is because of this. So, m times g will be g of not mass of the earth, but we have to take the mass of the earth which is inside this, inside mass. So, we will write this m inside by this distance. So, this distance becomes how much? r minus d whole square. So, into m. So, this m cancels. We have g, mass of inside is rho into 4 by 3 pi r minus d whole cube by here r minus d whole square. So, this term will get cancelled with this and only term left out will be this g into rho into 4 by 3 pi r minus d. Now, we can multiply this by r cube and here as r cube. Let us multiply this by r cube and this is suppose r cube. So, we get this rho into 4 by 3 pi r cube as the mass of earth. So, mass of earth means gm and it will be r times r minus d by this will be r, sorry, this here r won't be there, and so here r cube. So, r cube will be simply written as this r square, and now this term is g naught, that is g naught, the gravitational field on the surface of earth, into 1 minus d by r. This is the expression of g. Thus, g will be given as g naught 1 minus d by r. Now, let us learn the effect of rotation of earth on the gravity at different latitudes. So, this earth, our earth is here under rotation about its axis. So, this is the axis of rotation, Suppose we are at an angular position of theta, this place. So, here we have an object. So, you see, when we are here, then we have a normal reaction n acting in this direction. we will experience a gravitational force F gravity here, and there is a centrifugal force that is given by m omega square. This is r. Suppose this angle is theta, so this also theta. So this is r cos theta. So m omega square r cos theta. So you see here, this n is equal to, this n is equal to, that is n plus n together with the component of this, that is m omega square r cos theta. Then this angle is also theta. So again cos theta, so cos square theta is force due to gravity. So I will write then n, force due to this I will bring this side. So force due to gravity is here g mass of this m by radius of earth whole square, and then it will be minus m omega square r cos square theta. Now suppose n is the normal reaction, what we feel is mass times the effective gravity, that this value is here now m times g naught, where g naught is gravitational field. When I am here, the gravitational field is g naught, that is the field at the equator, minus m omega square r cos square theta. Cancels. So g at an angular position theta, at the latitude theta, is g naught minus omega square r cos square theta, where g naught is the acceleration due to gravity, acceleration due to gravity at the equator, at the equator. So the acceleration due to gravity is highest at the equator, and at the poles where this theta is 90 degree, this term will be more, so is the least. The acceleration due to gravity, acceleration due to gravity is maximum equator and minimum at the poles. This is how acceleration due to gravity varies with latitude, and this variation is because of the rotation of earth. Here r, let us write r as the capital R, so that it may not be confused with this r. R is the radius of earth and theta is the angle of the latitude, omega is the angular velocity. So angular velocity is omega.